Good day, I'm Dr. T and welcome to my office. So today I'd like to jump in and talk about disaccharides. So in this case, we're going to take two monosaccharides and stick them together. When we do this, we're going to stick them together in their ring form. At least one of them is going to need to be in its ring form because we're going to be forming an acetal. An acetal is essentially a carbon that has two ethers on it. So in order to form an acetal, first you have to form an hemiacetal, which is in the ring form. Okay, so disaccharide, we're going to take two monosaccharides and we're going to stick them together. Now there's a couple of caveats or a couple of things to think about when we stick them together. For starters, remember how when they form the ring form, they can go one way or the other, what I called alpha or beta? Well, when you have an alpha configuration, the oxygen that's sticking off of the anomeric carbon, that's the one that got formed from the carbonyl carbon, that one is kind of sticking off to the side, kind of downwards, so that when you form a bond, what we call a glycoside bond, when you form that bond, it's going to cause a bit of a twist in your carbohydrate. Whereas alternatively, if you have the oxygen coming in where it's sticking more or less straight out, what we call a beta, in that case it's going to give a nice linear glycoside bond. It turns out the alpha glycoside bonds are much easier for enzymes to break down. So typically most carbohydrates that you're going to be digesting are in the alpha, and those that you're not digesting are going to be in the beta, with one major exception for some people. And I'll get to that in a bit. Okay, now the other thing we need to discuss when looking at glycoside bond is which carbons are actually involved. So typically you're going to have your one monosaccharide and it's going to have whatever your anomeric carbon is. And for glucose, that's going to be one. In a lot of cases it's one. Fructose, it's not one because fructose is a ketose. So we're going to actually write this out. We're going to say, okay, is it in the alpha or the beta configuration? Then we're going to like, which carbon is my anomeric carbon? And then we're going to draw an arrow that indicates the bond. And then which carbon is it attaching to on the other monosaccharide? So for maltose, which is one of the simpler disaccharides, you've got two glucose molecules. And so you're going to have the one carbon of the first glucose, and it's going to have the glycoside bond to the 4 carbon of the second one. Basically, I like to think of it as head to tail. The 4 carbon is basically a tail. And that's going to be an alpha glycoside bond. Now, quite often you will see what's known as a Hawthorne projection. So in a Hawthorne projection, this is kind of a stylized hexagon. And to indicate that it's an alpha configuration, a Hawthorne projection will show the oxygen going down from the anomeric carbon. And down, by the way, is relative to where the number 6 carbon is. So in glucose, you form the ring. The number 5 carbon interacts with the carbonyl. So the number 6 is kind of sticking up like a little bit of a tail. So you got the one sticking up kind of as a tail. If it's going opposite, that's in the alpha configuration. If it's going the same, so it would be going up, that's the beta. But in reality, these are not nice, neat hexagons. They're going to be kind of more of a lumpy chair-shaped thing. So imagine like a 1970s, fancy, modern-esque, weird chair. Probably be an uncomfortable chair, but that's kind of what they're looking like. They can do a couple other configurations, but chairs are most preferred. Okay, so if you have that for maltose, it's going to do head to tail. And typically 1,4 glycoside bonds, very, very common. Now, you can do lactose. And so this is going to be like maltose, except for one of the monosaccharides is a galactose, not a glucose. So it's a distereoisomer. Very, very similar, but essentially all you're doing is rearranging one of the oxygens. And it's a beta glycoside bond. This has an important consequence. Lactose is actually fairly difficult to break down. You require a specialized enzyme called lactase in order to break down lactose. The root of the two words are the same. Os means sugar, ace means enzyme, hence the reason they sound very, very similar. Now, you're thinking, hey, wait a minute, I've heard of lactose, I've heard of lactase. Doesn't the pharmacy sell something called lactase? Yes, they do. So for the majority of humans, which if you are from a Western European or a Western/Northern European ancestry or North African ancestry or parts of India ancestry, This is going to seem a little bit weird, but the majority of humans can't drink milk. Most humans are lactose intolerant. And that's because most humans, most cats, most mammals of all types produce lactase when they're young and nursing, because the characteristic feature of a mammal is that their mothers produce milk for them as infants. And once they are weaned, they stop making lactase because you're no longer drinking your mother's milk. Well, a few humans, those kind of in regions that had some more cows, have a weird genetic mutation. It's called lactase persistence. We, and I'm lactase persistent myself, are capable of producing lactase along through adulthood. The amount of lactase we do produce does decline as we age, but nowhere near as much as most humans. And for us, we have access to a new food source, milk and dairy. Now, modern technology means that the rest of the world can join us. Even if they don't produce their own lactase, we can put it in a pill form and you just take the pill before you eat your ice cream or your pizza or all those wonderful, delicious dairy sources. And you can enjoy dairy like everyone else without having the lactase go into your intestines and all of the bacteria having a big old party, creating a bunch of gas, and not pleasant. But, hey, we got lactase, the enzyme to break that down. There's actually some interesting stories that I will put in a different video at some point that are kind of humorous and disturbing at the same time about lactose. But moving on, let's look at sucrose. This is going to be a glucose and a fructose. But unlike the last two disaccharides I talked about, these are actually going to form the aldehyde with both anomeric carbons. It's kind of a head-on reaction. And this actually has a really important feature to it. When the anomeric carbon is in an acetal, it's locked up. It can't do much. When it's in the hemiacetal, though, it can open up, exposing the carbonyl, which can do weird chemical reactions. As I mentioned previously, glucose has that aldehyde, and that's why diabetes is a thing. Well, fructose and glucose, if they're put head-on, so both anomeric carbons are in the acetal, then they can't open up. It's what we call a non-reducing sugar. It's not able to do a redox reaction with other random stuff. This is why plants don't get diabetes, even though, say, tree sap is just loaded with sucrose. Far, far more sucrose in sap than there is glucose in blood. Trees don't get diabetes. Sucrose is a non-reducing sugar because its anomeric carbons are completely locked up in acetals. Just about all of your other disaccharides and all your monosaccharides, those are reducing sugars. At least one of their anomeric carbons is not locked up in an acetal. Therefore, it can open up and start reacting. Now, with that said, if I look at, say, lactose, half my anomeric carbons are locked up in acetal, so that is actually a fairly major improvement. So an advantage for using that instead of just straight old glucose. Now, a couple quick points. One, if you're thinking, oh, so I can just consume sucrose to avoid getting diabetes. Yeah, no, your body will very quickly convert that into glucose, so that doesn't help. Other thing, we're talking about sugar. Sucrose is table sugar. That's, you know, your big 5-pound bag of light, sweet, delicious powder. Let's talk sweetness. So when you've got sugars, they have varying sweetnesses to them. Sucrose is kind of our baseline. It's usually given, you know, a unit of like 100 sweetness units. Other carbohydrates will typically be less sweet. So things like glucose are, you know, like a 60 or 50 or so. Fructose, that's actually significantly sweeter than sucrose. And that's actually one of the reasons why companies like to use fructose as a sweetener, because it's cheaper and you don't have to use as much of it. Or if you're serving an American audience, you can use a lot of it and it can be ridiculously sweet because we Americans love our ridiculously sweet food. Most countries don't like their food quite as sweet. Now, if you're looking at, say, what if I want a no-calorie sweetener or a low-calorie sweetener? Typically, by the way, they are very low, not zero. Well, in that case, the artificial sweeteners, the way that those achieve very low calories isn't the fact that they have any less calories per gram than sugar. It's instead the fact that they are ludicrously thousands of times sweeter than sucrose. Therefore, you need to use next to nothing of it. If you ever use the Splenda for baking, which looks very much like sucrose, except a couple of the alcohols have been replaced by chlorines, what's called sucralose, hard to pronounce, I will say. That, if you use the one for baking, you'll notice is insanely fluffy. And that's because they're trying to match a volume measurement when the weight measurement is really different. Thus, they need a very ultra low density material so that you can measure it with a measuring cup. But yeah, in general, artificial sweeteners, much more sweet, therefore they can use a lot less. This is also why soda, whether it be regular soda versus diet soda, have radically different mouthfeels, and why regular soda will freeze at a lower temperature than diet soda. So the Diet Coke will blow up in your freezer before the regular Coke does, so be forewarned. So with that said, have a wonderful day, and I'll see you in later videos.